DHCP, Dynamic Host Configuration Protocol. Okay, this is used to reduce the overhead of the network admin. Okay, why overhead? As the same case, if you are having, for suppose think that you are having some 1,000 pieces and you need to give IPs, you need to configure some basic configuration to all the devices in order to communicate. Will you go and do that basic configuration in every device? No. First thing is it will be overhead for the network admin who is configuring them. Second thing is there might be some human errors. There might be possible that some 1,000 pieces you are configuring. But supposing that you have given same IP some around 2 to 3 devices, it will be a problem. Human errors. The third thing is you cannot maintain a record to which PC did I give my this IP. And third thing is time will be saved, right? In order to save all this, we use DSCP. Okay, I'm concluding it. It will be very simple. DORA is a process where DHCP works on discover, offer, request, and acknowledgement. Okay, discover is sent by the client, whoever the device want to get the IP to the server. That I want one IP. Offer is the message sent by server to the client. You requested the IP, I'm sending you the IP. Request. Now it is the decision of the device whether it can accept or not. If it is accepting, it will tell that okay, I'm accepting the IP you sent. If it is having an IP, okay, at that time it will generate a request directly that I want this IP. Okay, a request. If it is accepting the IP, it will in request it will send that I'm accepting this IP. Or if it already has an IP, then it will request an IP that I'm having this IP and I'm using it. Okay. Now the server will send the acknowledgement. Use it. Okay. This is DORA and this is how a device will get an IP. You see, I'm telling you, this is not as simple as we discussed. If you want to read, it has many more things in it. If you are interested and if you want to do it, once let me know. I'll give you the material or suggest you the thing, whatever you can read. I'll suggest you. And by reading it, if you have any doubts, you can ask. Okay. This is DHCP. And yeah, one more thing. What if my DHCP fails? My DHCP has not given me the IP. Either at the time I requested, the device, the DHCP server might be switched off, or it might be in that case that in that situation that it cannot reply back. At that time, in Windows especially, in Windows PCs, you have an specific address range where the device itself will assign an IP. This PC has generated an IP to DHCP server. Now the DHCP server has not given the IP. Now why Windows machine, this machine will assign an IP to itself from a specific range. That range is called APIPA. Okay. This range has an IP range of 169.254.0.0 to sorry, yeah, 254.0.0 to 169.254.255. This is the address range used by APIPA. APIPA is automatic private IP address. Okay. Why APIPA is very simple to make a local area network devices make communicate. APIPA is So that is application layer. Okay. Now let's discuss the transport layer, network layer, and this will be finished. Yeah. So this is the network layer header IPv4. Actually, we have two versions of IP, that is IPv4 and IPv6, where both work at network layer. Okay, IPv4, this resides on layer 3 network layer of the OSI or the TCP IP. This is connectionless. If it wants to communicate the data, it will directly send the data. Okay, and this is the network layer header if we use IPv4. Okay, where version says what is the IP protocol version you are using, either version 4 or version 6, and this says what is the header length, not the total length of the packet. What is the length of my header, size of my header? Okay, TOS, it is like how to handle the packet. Okay, this is a not our cup of tea. It will be CCNA and CCNA level. Total length is the length of the whole packet along with the data. We have two lengths here: internet header length, total length. Okay, internet header length is only the header length. Basically, it will be of 20 bytes. Okay, only the header length from here to here. This size is mentioned in the internet header length. But if you are considering total length, it is including this header part and also the payload part. This combination is total length. Okay, that is total length. Identification. Yeah, as I told you, transport layer will do segmentation, right? Similarly, network layer will do fragmentation. I'll tell you. Fragmentation. Okay, fragmentation. What happens? In order to do the segmentation, it is checking MSS. In order to do fragmentation, it will check MTU. If the data, whatever it is receiving, it is more than the size of MTU, then it does fragmentation. That is same, dividing the whatever the data it received into small packets, and it will send out. Okay. So what this identification is used when it is doing fragmentation. Okay, when it is doing fragmentation, in order to tell the receiver that all these packets are belong to same packet, it will, in the identification field, it will give a value. For suppose one packet, it is divided into two packets, three packets. Now in the identification, it will have this value 1, 1, 1, 1. By seeing this identification on various packets, the receiving device will come to know that yes, these identification field of all these packets is same. So all these are need to be reassembled as one packet. Done. Yeah. And you have flags. Flags again regarding fragmentation, that will be not out of the fragment offset says what is the initial byte in my data field. Whatever data I'm carrying, what is my initial byte address that is mentioned in the fragment offset. See, I sent three packets. I did fragmentation. I sent three packets. Right. It came to know that these all three packets are belonged to only one packet. Now, how will it reassemble that? This packet is the first packet in that packet. This packet is the second packet. This packet is the third packet. How will it reassemble? Using fragment offset. First packet will have 0, second packet will have 1, third packet will have 2. Using this series, it will come to know that this is the order. This is used for fragment offset. TTL. TTL is you're sending the packet. Okay. And if there is a misconfiguration, loops will occur in the network layer. This device, it knows that in order to go to 10 network, it has to send the data to this device. This device was misconfigured, so it knows that in order to go to 10 network, the packet has to be sent to this device. This device knows that in order to go to 10 network, that the packet has to go to this interface. Now what happens? The packet is what? It is evolving in this itself, round and round and round and round and round. Will it have no depth? If there is no depth, if there is no time limit for that packet, it will keep on roaming in that loop itself. It will not die. What happens? The router keeps on processing the packet whenever it comes to it. Processing will be used, utilized, time is wasted. Third is there is no depth for the packet. In order to avoid this, you use TTL. What is TTL? A predefined value. Something Cisco uses a value of 120. No, 255. Okay, 255. Now this 255 is sent in this packet in this field. Whenever a device receives it, what it is? First, it reduces this value by 1. It says that it received it has crossed one hop, one router. So the device, the value has to be reduced. What happened? Now it got the packet. Now it got the packet with 255. When it is going, it will be 254. Now what it is? It will also reduce it and it will send it 253. Now it also got the packet. It will reduce it 252. When the packet, this TTL value becomes 0, the packet will be dropped. By this, what happened? Router processing is saved, time is not wasted, right? And the packet is dead. Loops are avoided. In order to do this, we use TTL. I told you protocol field already. Protocol field will tell what packet is being received, what is there in that packet, to which protocol should I give this packet. That is known with the help of protocol field. Header checksum, it is very similar to checking the errors. Whatever the header is generated, algorithm is run on it, and whatever the output it got, it is encapsulated here. The receiving device will check this checksum, right? And it will again run the algorithm on this header. The output and this value must be matching. Then only it will accept the packet. If not, it will drop the packet. Okay. And the source IP, destination IP, usual, and IP options. This is not on. Yep. Payload is the data. Whatever the data is received from the transport layer, it will be the payload. Or whatever the data it is receiving from the data link layer, it will be the no. Whatever the data it has to give to the what transport layer, it will be the payload.